Hi, welcome back. So in chapter 3, you must know add the outline of exponential function logarithm. So let's go ahead and explore the idea or the framework of exponential function and logarithm. The points are actually if you take any number, polynomial x for example, and raise it to a certain power, the idea is said to be that take the x multiplied by itself as many times the y is indicating. For example, a value of 2 and raise it to power of 3, number 2 and multiply by itself 3 times. And the actual image of this, taking the entity of counting of 2 by counting this unit twice. So this is 1 and this is 2. Now the outcome here that we see, it's the outcome of this product, 2 multiplied by 2, and the count of it is equal to 4. And then I take the product or the outcome of this and again multiply by 2. That means take the exact same entity as it is and count it twice. So now we have the total number of 8. Let's take this idea and by looking at axis or coordinate system of x and y as we have seen before. So if I would have x here and y here, if I have the input of 1 in here, I would like to get the outcome of 1. If I have 2, I would like to get 4. 3, I would like to get 9, and so on and so forth. Graph this, you will get something called the parabola or the line that we have learned about it before. It should looks like this. And if you were to go to another problem, for example, get input of 1, you get 1, input of 2, you get 8, input of 3, you get 27, etc. Maybe you get like some other kind of a line looks like this. The final function has been constructed that the outcome that we're looking at is just equal to 1 over 1, which represent that unique alpha, multiplied by the x raised to the power of that value that we're looking at. Based on changing of that, the line that we're trying to observe could then change. However, this time I'm going to show you another task that need also to be solved. If I would have to give you input of 1, I would like to get output of 0. 2, I'd like to get output of 1. 4, I would like to get output of 2. 8, I would like to get output of 3. 16, I'd like to get output of 4. 32, I would like to get output of 5. So the question is, could you think of a function that actually can illustrate the outcome of this behavior just like we did in the previous one? If you take, for example, y is equal, any input you like, and we're going to fix a value, we call it k, and let's say k is equal to. In this case, our real function here become y is equal, input you like, we will only raise it power of 2. And if we change k to be equal to 3, it means my new function will be y is equal x power of 3, and so on and so forth. As you are changing the power, the line will change. How about we do it other way around? Instead of fixing the k, we're gonna fix here a value v, and we're gonna then change power as you like. If v is equal, for example, 2, this function become y is equal 2 to the power of x. How about if v is equal 3? That means y becomes 3 to the power of x, and so on and so forth. So you see the difference between the two presentations. In this case, the base was changeable, but the power was fixed. In the other way around, that we fixed the base and we were changing as many power as we like. Let's try actually to, first of all, try to utilize the idea that we have just created here by taking a certain base, okay, and change the power as we like. You will get these points just like so. So you could see here 2 to the power of 1 is 2, you get 2 to the power of 2 is 4, power of 3 is 8, and so on and so forth. How about this case? I get 1, okay, I would like to get 0, 2 to get 1, and so on and so forth. Now if I want to graph these points I just showed you here, they would look like this. This, the task that we're trying to draw, and the previous one where we have fixed the base to be 2, that seems these points are actually the inverse of the previous point. If you look carefully here, this point it is 2 and 1. Look at this point is 1 and 2. Look at this point 4 and 2. 2 and 4. So it seems to be we're looking at the inverse. As we have created this function, which is y is equal 2 to the power of x, we would like to get an inverse to this to create such a new function, which later is going to be called the logarithm, of course. Now, the point I just wanted to show you, I think, in my opinion, the evolvement of logarithm, they came actually by understanding the meaning of power. Let's go ahead and try to actually construct such a logarithm. So you could see here the product that at each point, and I'm moving, product of multiplication of this particular base. On the other hand, a reference, if you like, imagine as an index. I will start this index like you're creating an array. We'll start that one with 0. So what happened here, I just was adding 1. It turns out that this line here, it's exactly to be this line here. And this vector here, it turns out to be the power I was manipulating here. So I think there is a relationship. That's exactly as if I want to take the behavior from other way around, the log of that particular base, where we get that value, is equal y. If we take this with a real example, 2 to the power of 3 is equal to 8. It's exactly as if we're saying log base of that 2, 8, is equal 3. This is the inverse of this. This new mechanism have made a lot of difference in the language of mathematics. Show you this once again. When the input was 16, I know that I raised 2 to the power of 4. So next what I would like to do I would like to show you some important property concerning this function. Now the first property it says the following. Say for example log of 2, 16, something like that. So arranging the 16 to be in a form of 2 and raise it to the power of 4, this term can cancel the base and then you leave with a value of 4. Now the second one, it says the following, that if you would have a base, for example, 2 is raised to log base 2 of 7, for example. Result of this term cancel this and the result is equal just 7. Now the third property, it says the following. Say for example, I get log 2, say m to the power of 6 multiplied by n to the power of 3. That is exactly as if log base 2 multiplied by m to the power of 6 plus log base 2 multiplied by n to the power of 3. Give you one more property that can be really handy and powerful as well. So you could see here it's subtraction, which is correspond to the division, and addition, it just correspond to the multiplication. And the last one taking the power, the term as a constant, and then do the log b of that m. Let's do some examples that maybe can make the picture quite a bit clear. Let's say, for example, I would have like a term, say 8 to the power of 2 plus x. We want to take log that is base 8. That's equal log base 8 as well, 2. So the both side, I just took the log for both of them. And why did I do that? Because I know the property that I can cancel this term as so, right? You will end up with the 2 plus x equal log base 8 of 2, which is 8 to a certain power of a value equal 2. This 8 could be 2 power of a 3, and of course this will be multiplied by the v anyway, equal 2 power of 1 anyway. 3v is just equal to 1. In this case, v is just equal 1 over that 3. That is 2 plus x is just equal 1 over 3. Will lead you to the value minus 5 over 3. Now we saw the actual graph of this function. It is always 1. It will always be 1. So 0.66 divided by 0.66 is 1. Now in this equation, the slope was 2, 4, 6 of each point. These are the points, right? Now if you take a ratio, 4 over 2 is 2. 6 over 4 is 1.5. We are approaching somehow close to the value of 1. As you go up on the value, as the function is proceeding more and more, it seems this behavior of banding is getting to be more and more straight line. And that's exactly the meaning of this number. The ratios is changing from 2.1.5 and getting closer and closer to 1. Now again, when we take the ratio between these numbers, like 12 over 3 is 4, which is 2.22, then 1.7, 1.5, 1.4. So you see, we are diverging towards the value of 1. Just now we have discovered a pattern when we have the case where the indeterminate or the base is indeterminate, but the power is constant, like power of 2 only, power of 3 only, but the base is changeable. Let's now move to the second stage, this idea. All right, see you then.